Hello everyone, my name is Mamta, Assistant Professor in Mechanical Engineering Department, Maharashtra University. Today I will be discussing about hydraulic turbines. It is one of the common topic of fluid machines. So these are the contents which I'm going to cover in my presentation, that is introduction and what are the types of turbines, then what is the principal operation, how hydraulic machine works actually. Then we will be classifying the turbines, various types of turbines basically. So hydraulic turbine. A hydraulic turbine is a type of turbine that is driven by the flow of water or other fluids. It is commonly used in hydroelectric power plants to generate electricity from the energy of falling water. Okay. So the hydraulic turbines basically are the devices that convert the potential energy of water into mechanical energy. Hydraulic turbines is one of the useful applications of mechanical energy. These have been utilized to produce electricity from sustainable resources and remain a significant component of the worldwide energy blend. Water can store potential energy in a hydraulic turbine, which is the energy that is stored in a body due to its position or elevation relative to the reference point. So when the water falls from higher elevation to lower elevation, it gives kinetic energy, which is the energy of motion. Kinetic energy of the falling water, it is used to drive the turbine and generate electricity. Amount of energy that can be stored in water, it depends on the head and the flow rate of turbine of water. Head is basically the vertical distance between the water intake and turbine. Higher the head and the greater the flow rate, the more energy can be extracted from the water. So hydraulic turbines, these are particularly well suited for generating electricity from water because water is dense and easily transportable energy storage medium. Unlike batteries or other storage technologies, water can be stored in large quantities and released as needed to generate electricity on demand. This makes hydraulic turbines a reliable and flexible source of renewable energy. So these are the principal operation, how hydraulic machine works. Here we will be discussing the basic components of hydraulic turbine, which includes runner, which is the rotating part of the turbine that is driven by the water flow, and the stationary part, which is wheels and shaft tube is basically here, the tail is. The casing contains the runner and is designed to direct the water flow onto the runner blade. Casing and the guide vanes are adjustable vanes that are used to regulate the water flow and optimize turbine performance. Shaft tube is tapered tube. It is a tapered tube kind of that connects the runner to the tailways, and it is designed to reduce the velocity of water leaving the turbine, which helps to increase turbine efficiency. So, layout of hydraulic turbine, it can vary depending on the specific design of turbine and the type of power plant in which it is installed. However, there are several key components that are common to most hydraulic layouts. That is intake. This is the point at which water enters the turbine. That is intake when the water enters the turbine. This is the point. Okay. So then we have the intake may be located at the base of dam or in a canal or pipe that delivers water to the turbine. Then we have pen stove. This is a pen stove. This is the thing that is pen stove. This is a large pipe or conduit that carries the water from the intake to the turbine. The pen stove is designed to maintain a consistent flow of water and pressure to the turbine. Then we have turbine. This is the turbine. Okay, these are basically turbine. It is the heart of hydraulic power generation system. It is typically located in a large concrete or steel structure known as a powerhouse. The turbine consists of a set of blades or buckets. These are buckets basically, and, um, or blades we can say that are mounted on a shaft and are rotated by the force of water flowing through them. Then we have generator. It is located besides the turbine. Then generator is located in the same structure as the turbine and it is connected to the shaft of the turbine. It converts the mechanical energy of the rotating shaft into electrical energy that can be transmitted to the grid. Then we have tail race. After the water passes, this is tail race. After the water passes through the turbine, it is discharged into a channel or river called tail race. Tail race it is designed to return the water to the natural waterway at a lower energy level. Then we have control system. Control system is it is used to monitor and regulate the flow of water and the speed of turbine. This ensures that turbine operates at optimal efficiency and prevents damage to the equipment. Okay, control system is controls and monitors the flow of water basically. So the layout of hydraulic turbine is designed to optimize the flow of water and to minimize energy losses in the system. By carefully controlling the flow of water and speed of turbine, hydraulic turbines can generate large amount of clean and renewable energy. Okay, now move on to the next slide. So hydraulic turbines can be classified based on the several different criteria, including their specific design features, operating characteristics, and application. So these are also some of the most common ways of classifying hydraulic turbines. Okay, so we have design type. Then we have design type. There are several different types of hydraulic turbines we have, including the Pelton turbine, Francis turbine, Kaplan turbine, and cross flow turbine. So each type has its own unique design feature and it is suited for a specific operating condition. Then we have head range. So hydraulic turbines can be classified based on the range of head, the vertical distance between the turbine or the water source. It is the vertical distance between the turbine and the water source. So they are designed to operate under the range of head. Then, for example, we can say low head turbines are designed for head of less than 20 meters, while the high head turbines are designed for the heads of more than 200 meters. Okay, then we have flow rate. So, if yeah, the turbine can also be classified based on the flow rate of water. This can designed to uh, handle the flow rate. For example, the low flow turbine designed for flow rate of less than 2.5 cubic meter per second. Then we have while we have high flow turbines which are designed for more than 10 cubic meters per second. Then we have applications, different applications. Uh, from the different applications, we can classify based on the uh, we have, for example, turbines are designed for the use of large-scale hydraulic power plant, while others are used in smaller scale applications, for example, irrigation system or small-scale hydroelectric also. Then we have turbine orientation. So finally, turbines can also be classified based on the orientation also related to the water flow. For example, vertical axis turbines we have when the axis of rotation perpendicular to the water flow, and other is horizontal axis turbines. Those have the axis of rotation parallel to the water flow. Now, next sixth is the number of runners. Some hydraulic turbines have multiple runners or sets of blades that rotate around the central shaft. So these turbines are called as multiple runner turbines and are used for the high flow rates. Then we have specific speed. Specific speed it is a dimensionless parameter that is used to characterize the performance of hydraulic turbines. So turbines can be classified as low, medium, or high specific speed depending on their design and operating characteristics. Then we have operating mode. Turbines, it can be classified based on the mode of operation, such as constant speed or variable speed. So in variable speed turbines, it is becoming increasingly popular in modern hydraulic power plants because these variable speed turbines they offer greater flexibility and control. Next, we have ninth installation type. So these turbines can be classified based on the way they are installed, such as vertical and horizontal. So vertical turbines are typically used for the low flow, high head application, while horizontal turbines are more common in large hydroelectric power plants. Okay, and then we have last is the material of construction. This is also a common type of classification we have. It is classified based on the materials used to construct them, such as steel, cast iron, composites. Uh, it is new to us, right? The choice of material depends on factors such as operating conditions and intended lifespan of turbine. So these classifications are just some of the many ways that hydraulic turbine can be categorized. Also, these classifications are not mutually exclusive and can overlap with each other. That means, I mean, it is depending on the specific turbine being we are using. Okay, we are working on. Next we have a slide of main classification of hydraulic turbine. Okay, so it is based on the type of action basically that water has on the turbine blades. So we have three main types of hydraulic turbines based on the this criteria. So we have impulse turbine, reaction turbine, and cross flow turbine. So this is the impulse turbine. In impulse turbine, the water strikes the turbine blade with a high velocity jet. The blades are designed to direct the water jets so that it changes direction and imparts a force to the one type of impulse turbine is the Pelton turbine, which uses a single jet of water to drive the turbine blades. Impulse turbines are typically used in high-head, low-flow applications. One example of a site where an impulse turbine might be used in a mountainous region with a deep river or stream. Fulton turbine, it could be used to generate electricity from high altitude mountain streams. And one of the example in India, it is commonly used in Shimla. Uh, Shimla is located in the Himalayan region, and uh, it is home to several small hydropower plants that use Pelton turbines to generate electricity from high altitude mountain streams. Okay, so these plants provide electricity to the local community and help to reduce the city dependence on fossil fuels. Okay. Hmm. Okay, this plant, that Shimla that uses Slender turbine is the Baspa second hydroelectric power plant. Okay, so next we have is reaction turbine. So in the reaction turbine, the water flows over the turbine blades and fills the blade channel. The pressure on the water on the blade generates a force that rotates the turbine shaft. The most common types of reaction turbines are the Francis turbines and Captain turbines. Reaction turbines, these are typically used in low head, high flow applications. An example for site where the reaction turbines can be used is a large river with a moderate flow rate and a low head. And it might be used in hydroelectric power plant located downstream from the dam or reservoir. Okay, it is the reaction turbine commonly used in Sri Salem. It is located on the Krishna River and it is home to a large hydroelectric power plant that uses Francis turbine to generate electricity. Okay, then we have cross flow turbines. This is the cross flow turbine, and these are the types of reaction turbine that use water flowing across the blade instead of along them. Blades of a cross-flow turbines that are curved and are arranged in a cylindrical shape as the water flows across the blade and it creates a pressure difference that drives the turbine. Cross-flow turbines are often used in small-scale hydropower systems and in applications where low maintenance and high reliability are important. Okay, it is used in small irrigation channel or a municipal water supply system. Okay, so cross flow turbines, it could be used to generate electricity from water flowing through a water supply pipeline. The common example of cross flow turbines is used in Coimbatore. Okay, so here the cross-flow turbines are used in small-scale hydropower systems to generate electricity from irrigation canals. So these turbines help to reduce the city's dependence on fossil fuels, as we already told you. Okay, and provide a reliable source of clean energy for the local farmers. So it is important to note that the choice of turbine type will depend on a variety of factors, including the specific site condition, flow rate, head of water, and the desired output of the system. So engineers and designers, they must be carefully evaluate these factors when selecting the most appropriate turbine for a particular application in any city in India or other. Okay, so that was it. This was it from my side. Thank you so much for your patience and listen. Thank you.